But today we're here to celebrate math. And so I would like to introduce my great colleagues who it's a pleasure and a privilege to serve. Anthony Barcelo for math, and I'll let you take it. Thank you.
Thank you, Amanda. Okay, who's on the lights? Let's bring the lights down a little so that people can actually see this and can't see me. Much better, thank you. Thank you. As Amanda told you, I'm Tony Barcelos from the math department, and I was concerned about the turnout. I see the room is a little crowded. I did caution my colleagues from the math department not to create any scenes, and at least we can tell they will not be doing the wave. So we should be, actually Matt can do the wave all by himself. Brett, keep it.
You know the two old men in the monks.
Okay, I know where this is going. I plan to insult your intelligence quite deeply, because the math that's going to appear on the screen is going to be extremely simple. So you will grasp it immediately and you say to yourself, I know that. Why is he telling me this? Because I know this already. Well, that's the theme. You're already a math genius in that you know these basics, but you may not know what you know in the sense that these things have a lot more significance than you might realize. So let's start off by looking at a particular genius, an undeniable genius. All of you will recognize him immediately, right? You all recognize him immediately? You recognize him? Yes, everyone recognizes Galileo Galileo. Oh, wait a minute, that's wrong. It's Galileo Galilei. I think that's a lyric from something. Okay. Everyone knows about Galileo. Everyone knows that he's famous for some reason. If you know about his fame, you probably are aware that when he got his first telescope, he didn't use it to spy on the neighbors. He tilted it up and looked at the sky. And the 4 Galilean satellites of Jupiter, 4 moons of Jupiter, are named the Galilean satellites because he saw them. He saw them, he could tell from night after night that they were orbiting Jupiter, and this messed up the whole plan where everything was supposed to orbit the Earth. This was disturbing, but Galileo documented his work and published all kinds of amazing things about the heliocentric theory. Heliocentric as opposed to geocentric. You know, heliocentric centers the Earth. Geocentric center is heliocentric for the Sun, geocentric for the Earth, and then my college roommate, egocentric, because he was the center of the universe. Center of the universe is currently living in San Diego. All right. So this was a big deal, and you know he got in trouble. Well, let's talk about some of the things he discovered that didn't have to do with the system of the solar system. Let's talk about physics at its basic. And let's start off with one of the simplest things I can think of. Here is math you know. Area of a rectangle is length times width. We all know that, right? God, it's easy being a math genius. And you can even draw a picture. Oh, look. 4 by 3, and you can even count them. There's 12 square units. That's pretty easy. Everyone knows that. Length times width, a simple product for area. We use simple products for other things. Distance equals rate times time. Rate times time is one of the great fun things that you did in algebra. Remember how much you enjoyed distance, rate, and time problems? And trains leaving Chicago for some reason. Everyone wanted to leave Chicago. Here's an example. I tell my algebra students, or my pre-algebra students, that they all know that if they travel at 60 miles an hour, if they ever do that, for 3 hours, you go 180 miles. We all understand this kind of math on an intuitive level, and it's kind of unfortunate we don't understand the process that underlies it because we think it's all instantly intuitive and there's nothing fancy going on. Actually, it's fairly clever. So if you started off 60 miles an hour, 3 hours, 180 miles, where would that get us? Oh, Fresno. Okay, well, you know, these things happen. I go to Fresno fairly frequently. I have family down there. I keep them where I can find them easily. This is the same graph, except, you know, I did a rectangle thing, and now I bootlegged a coordinate system into it, and now it's harder. No, it's not harder. You've got a t-axis. This is a velocity time graph. And 60 miles an hour for 3 hours, and you have 180. So far, no one is challenged by any of this. You're all thinking, I totally understand this. We need it to be more exciting. So, wow, now it's more exciting. No, I don't know that that's more exciting. But this is a different trip. See velocity? It's down here at 0. And it gradually climbs to 60 over the course of 3 hours. First hour up to 20, second hour up to 40, now we're up to 30. And it's just half the rectangle that we had before. Do you all agree that 1/2 base times height is a perfectly good way to find the area of that triangle? And that area still represents distance traveled. It still represents distance traveled, and now it's 1/2 times 60 miles per hour times 3 hours. So what's that blue stuff? What distance are we talking about now? All of you math geniuses can tell me immediately what it is. Any math genius present. It's not 180 anymore. It's now 90. Thank you. Thank you. Okay, so please control yourselves. All right, 90. So where does that get us? God, we can't win. All right, let's move on. Okay, so we're taking a look at this guy again. It's the same graph. I've made one tiny little change. One tiny little change. I added this. So be careful not to panic. It's just saying that for every hour, you put on another 20 miles per hour. So, like I said, after the first hour, you're going 20. After 2 hours, you're going 40. After 3 hours, you're going 60. So we're just taking this number down here, t, whatever t is, and plugging it in here, and that tells you how fast you're going. Does anyone know what it means to talk about gaining 20 miles per hour? What's that all about? When you talk about speeding up, the word for that is acceleration. And everyone knows what acceleration is. Acceleration is the feeling that you get when you speed up and you're pressed back in the driver's seat. And your passengers are too. All right, so we have this nice little formula. We put this together. And we're talking about acceleration. Acceleration is this number right here, this 20, which is, for all of you people who remember a little bit of algebra, it's basically your slope. I also want to point out that this is not a realistic trip. This trip to Turlock, initially, you are so reluctant to get there that you're going near 0 miles an hour, but eventually you're up to 20. Okay, this is going to be a really exciting trip on Highway 99, right? You're going down 99, and after an hour, you're all the way up to 20 miles an hour. Okay? And by this point, you might be kind of excited because, you know, you're looking at the road from under the steering wheel, peering at the road as you speed up, and eventually you get up to 40 and then 60. I'm going to make a comment about the earlier trip because I'm making fun of this trip as unrealistic. Well, if we go back to this trip, 60 miles an hour all the time, at the beginning of the trip, you're going 60 miles an hour. So I guess you jumped into a speeding car at that point. You realize that mathematical models are a little bit artificial because in reality, I realize we have cruise control now, so you can lock the speed and never vary, but in reality, most of the time we speed up and slow down. So things get kind of wiggly, and it gets harder and harder to compute this blue area. But that didn't stop Galileo, remember him? that didn't stop Galileo from getting some fundamental computations done, which we're going to see in just a minute. So let's go forward again. Welcome to Turlock. And there's that. Okay, so there's that formula. And bear with me as we make things abstract. Here's time, this entire base right here. And after t hours, you're going a times t. Remember, a was the acceleration, the slope of this guy. And then this blue distance is going to be 1/2 this height times that base. Basically multiplying base and height. So it's getting more exciting now. 1/2 at squared is the distance for constant acceleration. If you are speeding up at a constant rate, if your acceleration is constant, you end up with this triangular distance graph. And that blue space, that blue mileage, or whatever units you're using, it will tell you that's how far down you get, starting with that constant acceleration. This is a lot more complicated than just distance equals rate times time. A lot more complicated, a little more complicated. So now that all the math geniuses here are completely, excuse me for this, I apologize, up to speed. I know, that was really good, wasn't it? I shouldn't have telegraphed that, but. So there's that formula. I did it big, that's so I wouldn't shout. Who knows why I did this? Yes, sir.
Gravity.
Gravity. Yeah, that's heavy, man. All right, so now I'm edging back toward Galileo. Galileo was the guy who started figuring out the laws of physics, in particular that 1/2 at squared thing. But here's a teensy little problem. I'm going to click one more time and replace G with 32. How come I got 16? What happened? Oh, there's a 1/2. Okay? And math geniuses understand that when you take 32 and multiply by 1/2, you get 16. I apologize for the units. These are British imperial units. This is if you're talking about feet and seconds, because gravitational acceleration on the Earth is 32 feet per second, approximately. And so you may know British imperial units, very influential. Even the British don't use them anymore. They've gone metric. But it is kind of convenient. We have a nice round number here. That's how far something falls under the influence of gravity in free fall. You let something go, and that's how fast it travels. How fast it travels, how far it goes. The longer you let something drop, the faster it speeds up. It accelerates. Gravity is constant acceleration. And for all of you who are really old, if you remember the space program when the astronauts went to the moon, on atop the Saturn 4B third stage, and they got up to something like 25,000 miles per second. They were going really fast. 7 miles per second, I think, is what it is. I meant to say per hour. Okay, so let's talk about 7 miles per second. They had to speed up to get there. And while they were speeding up, they were pressed back in their acceleration couches. And they were experiencing several G's of acceleration. 1 G of acceleration, you feel like you're on the Earth. When you're experiencing several G's of acceleration, your face wants to peel back, and you stop being able to take deep breaths. So the astronauts all trained to get through this. They had a lot of acceleration, several G's of acceleration. Now let's talk about Galileo and how he figured this out. Because Galileo was in the era before stopwatches. And if you take something and simply drop it, it goes kind of fast. It's difficult to measure. You want to do splits on it, right? Like if you had a time-lapse photograph so you could measure things. He didn't have any of that. He had his pulse. And there were indications that it was a problem for him to do his experiments because he kept getting excited watching these things happen. And he had to stay calm. So if you're a scientist in the 15 and 1600s and you want to study free fall, and if you want to figure out how gravity operates on a freely falling object, what do? Well, if you're a genius, perhaps slightly more of a genius than those of us here, you slow down gravity. What the hell is that? That is Galileo's inclined plane. If you've never seen this before, take a gander at that and appreciate a scientific instrument from a few hundred years ago. Today they'd be made out of aluminum and plastic, but in those days they did some nice carpentry work on this. By using an inclined plane, instead of simply dropping something, Galileo figured that he could roll it down an inclined plane and attenuate gravity, retard gravity, slow gravity down. And that's a pretty clever thing to do. Here's a little schematic. Acceleration. It speeds up every second. It travels farther and farther. And if you had one of these inclined planes where things slow down and instead of kerplunk it hits the ground quickly, it slowly rolls down the inclined plane. Yeah, it's speeding up. But now you can measure things. You can mark stuff on the inclined plane. And notice these intervals. Okay, check those out. If you go back to look at Galileo's instrument, there are the markers. This is obviously not Mark 1. Okay, this is not his first version. After he worked with it, he knew where to put the spacers to indicate when the ball is rolling through. By the way, do you notice what's on each of these little hoops? Can you tell? Little bells. You roll the ball down and it goes ding, ding, ding. And he thought that was kind of cool. All right? And because they're spaced apart, they were supposed to ring at uniform intervals. Because it's going faster, so they needed to be farther apart. So if you listen to the ball going down the inclined plane, you were supposed to hear evenly spaced rings of the bell. And he could, adjust these until he had this lovely spacing, which I borrowed this from the University of British Columbia, where someone did this graph for his physics class. And notice the distance increases much faster. It's because it's a square. Well then, where do you go from there? Well, let's go back to this guy. Falling on Earth. All right? If you are from a different planet, your falling rate may vary. But not while you're on Earth. Let's talk about what happens if you fall for 1 second. What's 1 times 1? Times 16. You will fall 16 feet. Okay? If you fall for 2 seconds, what's 2 times 2? 4. 4 times 16? 4 times 16? 64. Okay, so you fall 64 feet in 2 seconds. Oh, thank goodness for Excel. This first unlabeled column. Okay, math geniuses, tell me what the first column represents. Time in seconds, yeah. And this one represents how far you've fallen. Well, at 0 you haven't fallen. Then you fall in 16. Now you fall in 64. 144, that's next, and it keeps on going. And this guy, this last column. Let's suppose that I got Matt to volunteer for a falling object experiment, and I put him up on a cliff 1,024 feet tall. Okay? And then we push him off. After 1 second, he's fallen 16 feet. He's now at 1,008 feet in altitude. So basically what's going on, I'm just taking this away from 64. And after 8 seconds, kerplunk, or splash, or some smashing pumpkin sound. Did you know Galileo liked to drop things from stuff? In particular, there is the story, we don't know how true it is, but about the Leaning Tower of Pisa, where he goes with 2 weights and lets them drop, and they fall down, and they land at the same time, because you never saw anything about mass or weight in here. Things just fall under gravity. There are some assumptions. The assumptions are very simple. The assumptions tell you things like, well, first of all, assume there's no air, because it gets in the way. Okay? The other thing is that assume gravity is uniform, as if the Earth is completely uniform instead of having mass concentrations. Did you know that gravity is slightly different in different places? Check to see where Jenny Craig builds her spas. Okay. And the other thing we assume, and this is a bit of a problem, when you're going to operate over a wide range, you're assuming the Earth is flat. Fortunately, given the internet these days, people who believe that have found each other and have been making videos that you can watch on YouTube proving the Earth is flat. But it's not. It's an approximation. Who knows the name of David Scott? David Scott. Anyone know who he is? Any suspicions? How about if I mention Apollo 15? Dave Scott is the commander of the Apollo 15 moon mission, who, pointing out that the moon has no air, one of the assumptions that we have to make about ballistics on Earth that we don't have to make. Now, Galileo used lead weights. They have very little air resistance. They just pile on through. And if they're heavy or they're relatively light, they still go to the bottom in almost exactly the same time. Dave Scott had a hammer. If he had a hammer, he could hammer geological samples. So that was from his astronaut exploration kit. And in his pocket, on his own volition, he took a souvenir. He took a feather. And he dropped them at the same time in front of a camera during a transmission to Earth. And feathers don't float in vacuum. The feather and the hammer hit the lunar surface at the same time. It was a Galileo experiment done on the moon in the absence of air in vacuum. So that was kind of cool. Really, Dave was going Alan Shepard one better, because on Apollo 14, Alan Shepard took a golf club and a golf ball and teed off. And somewhere on the moon, there is a golf ball that Alan Shepard blew over the horizon. Best drive ever. Okay, let's move on from this one, the falling object, because I have just a few more tiny little interesting things to point out, because I'm supposed to be telling you the secrets of the universe in here. And all we have so far is a bit of a grasp on gravity. Here's a graph. This is my same table here, right? And here's the fall, okay? So down you go. And math geniuses recognize that shape. That shape is, what's that called? That is called a parabola. Yeah, have you ever noticed how mathematicians keep stealing words from people? Yeah. For example, you've heard of the word hyperbole. When an English professor tells you to avoid hyperbole, he or she is telling you what?
Don't over-exaggerate.
Don't exaggerate, or in particular, don't over-exaggerate. Exaggerate just the right amount. So hyperbole. Well, in math, a hyperbola is a geometric shape, and in astronomy or celestial mechanics, a hyperbolic orbit is an orbit being followed by an object that's going faster than escape velocity. In other words, if something goes by the Earth in a so-called hyperbolic orbit, that means it's going so fast that it can't be captured by the Earth. It has more than escape velocity. And you may have heard the word parable. A parable is a story about something that's supposed to make a point. Well, a parabola is one step down from a hyperbola. A parabolic orbit, you know, something that is shaped like this. By the way, if you take it back and consider its symmetry with the t squared term, nice beautiful U shape. If something goes whizzing by on a parabolic orbit, that means it's traveling at exactly escape velocity, just fast enough to whiz on by and keep on going and never come back. And if you were an astronomer, an observational astronomer, and you see something, you say, I would like to announce that this object is traveling at parabolic speed. And you know what everyone would say? To how many decimal places? Because if it's just a little bit short, then it's on a giant ellipse. That sucker's going to come back. If it's a little bit high, then it's not a parabola. It's just a stretched out hyperbola. That is exact. No room for error. And I'll tell you this much more. To date, astronomers have never spotted a comet on a parabolic orbit. Every time they see a comet, it looks like it's probably an ellipse that goes way back out to the edge of the solar system and back. There's never been a confirmed sighting of something going at hyperbolic speeds. In other words, visiting the solar system and never coming back. All right, so parabolas. Remember that bit about destroying your enemies? Okay. A lot of mathematics is devoted to this objective. And here are some parabolas. Look at that. Nice parabolas, huh? If you throw an object in the air, it comes to Earth, and we kind of know where. Because when you throw an object ballistically, words again. What does it mean when you say, oh, he went ballistic? When you say someone went ballistic, you're saying that crazy. Here's the thing. It means they lost control. They were out of control. When you throw a rock or a baseball or most anything, an algebra book, you don't control its flight. The moment you let go, it is in ballistic motion. And it's going to make a parabola. It's going to make a parabola shape. So you have yourself a nice cannon, a convenient little backyard howitzer, whatever you may have. When you fire it, the moment the projectile leaves the barrel, it's in ballistic motion, and it is making a parabola. If you go online and Google ballistics or ballistic tables, you will discover an incredible list specific to various sorts of weaponry, saying that here's the inclination you use to get this distance downrange. It's really quite awesome. This one I like because the artist did two things. He drew parabolas, but he drew them in pairs. Look at this guy. 15 degrees, kind of shallow. What's this one? Oh, 75 degrees. What do you call 2 degrees that add up to 90? Complements, yeah. It turns out that if you're firing at an enemy who's right here, there's someone you don't like who's right here. Well, you can loft it high and bring it down right on top of your enemy. It gives him quite a bit of time to prepare, but you know, if he has some kind of rampart in front of him, if he's dug in, come in straight down. Surprise. Or, if you simply want to get him pretty straight on, and he's just standing there, you can fire low. And by the way, because of the symmetry of this, whatever the muzzle velocity is right here, when it hits the target at the other end, it's going to have essentially that same velocity back. Think about the one that goes way up high. Gravity time. Fighting gravity, gravity's slowly stopping it, and right up here. Okay? And if you were a coyote, you would stop for a while and look around before you realize something went terribly wrong. But if you're just a projectile, you immediately start back, and you're speeding up, speeding up, speeding up, and by the time you get here, your speed is just about the same as it was at the moment of firing. So I like that one. While I was looking, I also grabbed this one. And now you can see a whole collection of ranges in meters. So this is a small sort of pocket-sized piece of weaponry because you can only get a few thousand meters down range. But this one is also working out the altitude, the maximum height. Every bit of this can be computed with algebra. Basic algebra can do all of these things. They can't, however, take into account air resistance. And that takes you to a whole nother realm of mathematics. You start doing differential equations and figuring out stuff like that. We're not going to go there. And as long as we're talking about weaponry, I had to do this. I can't help myself. My senior year, when I was going to school in Pasadena, the people in Fleming House, I was affiliated with Fleming House, went to Southwest Academy in San Marino. Southwest Academy was one of these military-type boarding schools where all the kids were dressed as cadets. And they had this 1812, War of 1812 cannon in their front yard on a pedestal. And my classmates went and stole it and brought it on campus. And it was plugged with concrete, and the spokes were nearly rotten. So some of the carpentry skilled students in Fleming House went to the Southwest Academy in San Marino in the middle of the night and repaired the spokes. They were working, repairing the cannon for a few nights. And after it was ready to go, several dozen students, there were over 100 members of Fleming House, a few dozen students or several dozen students went and took ropes and towed that through the streets of Pasadena and put it in front of Fleming House, where the next morning the people in the other student houses got up and realized that Fleming House ruled, and there was just no question about that. They removed the concrete, they fired that sucker. They put it back in working condition. And there was a series of disarmament talks with the administration. Behold the administration building. We have a yearbook photo, class of 73. Fleming House put in its section of the yearbook a photograph of Troop Hall, half destroyed in the background at the end of the Olive Walk, and in front there's a picture of the cannon pointing at the admin building. And my classmates are standing around it looking like militants. And it wasn't in the yearbook, but it was occasionally said on campus, "Suck this, Berkeley," because our administration building has been destroyed. To tell the truth, I probably should make a full disclosure. You guys know about the Northridge earthquake? Yeah, it destroyed or damaged some of the buildings on the Caltech campus in 1970. And our admin building was condemned, and during my senior year they tore it down, and during my senior year my classmates stole the cannon, and it was irresistible to set up a photo op. Okay, well let's turn away from that. I need to up the ante just a bit. Newton's cannon. This is a little zoomed in, so it's a little bit fuzzy, but Newton imagined a cannon on top of a mountain and firing it and firing it and firing it until eventually it would miss the horizon. Because it goes farther and farther, until at some point it's going fast enough to where it just goes all the way around and hits you in the back. Oh, wait a minute. He allowed himself a little clearance. That was wise. Have you ever seen this illustration before? Newton is famous for his law of gravitation, Newton's law of gravity, which involves the acceleration of gravity in the attraction between two objects. And by the way, there are lots of squares in it. It's an inverse square law. You saw a square figuring very importantly in the whole business of a falling object. Well, it figures in this too. And so Newton was talking about orbital mechanics. And let's bring him on stage. There he is. And there's the picture. This is a spread from his Principia Mathematica, which is apparently an important book that most people haven't read. It was all about his theory of gravitation, his theory of the solar system. Anyone know what he stuck on at the end as just sort of a little postscript? He invented calculus, and he tucked it at the end of the book, just in case anyone was interested in how he had done this stuff. As someone once said, would Newton have been able to do all of this if he hadn't been smart? I think the answer to that is no. And we aren't math geniuses at his level, but let's appreciate this. Calculus students here, and also those taking AP calculus in high school, they are learning stuff that Newton invented back in the 1600s. So they can do stuff that it used to take the greatest minds on the earth to do. But we have advanced to such a point that we have a grasp on some of this. And to sort of bring this to a close, look at that sucker. Do you see the parabola? This dish is a parabolic dish antenna. And you have seen parabolic dishes all over the place. For things like, anyone have an idea? Satellite TV. Those dishes that you see sprouting up, or microwave relay towers, parabolic dishes. We don't see those because a lot of them, they're enclosed from the elements, but inside there's a parabolic dish antenna. And this is the Very Large Array. Anyone ever seen this? You know where it is? It's in New Mexico. Okay, it's in Socorro, in the desert, south part of the state. And years ago, I got to climb around inside one of these. This is like 82 feet across, or 25 meters for those of you who've gone metric. And you see this guy? Here's a guy about 6 feet tall right here. And remember, he's closer. If he was back here, he'd be a little bit smaller and he'd be on this staircase so that you can climb up and get inside if you're a maintenance guy. The parabolic dish antenna does what? It uses the power of the parabola, the same shape for falling objects. The same shape for falling objects will also gather and focus electromagnetic rays like radio waves right there. They come in, they bounce off, and they collect there, and they watch the skies. Oh, I just said watch the skies again. I said that earlier. What was that earlier context? Galileo. Yeah, looking up is apparently a good thing. Okay? And I wish more of my students would do that so they wouldn't be texting so much. But this is where I'm going to stop it. The Very Large Array accepts visitors. If you're ever traveling in New Mexico and you're cutting across the desert, take a detour. Go see the Very Large Array. It's hard to grasp it from a single photograph, even when you get the scale of it. There are 27 of these radio telescope antennas. They're on a 3-spoke array with railroad tracks. And it turns out that, oh, see these guys? Here's one, here's one, here's one, here's one, here's one, here's one, fading off into the distance. And the radio astronomers, when they want to focus it, they don't do it, but their staff goes out and remounts the antennas closer together or farther apart. It's not, you don't twiddle a knob and focus this guy. It takes a couple of days of dismounting and remounting these guys. And secrets of the universe come into those dishes. If you have any comments about the secrets of the universe, you can email me. I am an instructor here on campus, so you can email me at barcella@arc.losrios.edu. And a year ago, I got anthonybarcelos.com as my own personal website, which has some of the secrets of the universe on it. Does this work? Oh, it does. I spoke too soon. I probably should wait. Several add-ons are ready for use. Don't enable. Don't enable, go away. That's the end of it, folks. If you want to get in touch with me because you have brilliant questions from your genius minds, I will appreciate the opportunity to respond to them. I thank you for your attention, and I hope you had a reasonably good time being math geniuses for 40 minutes. Thank you.